exponential functions, y is equal to e to the power of x. E is a special mathematical constant, and the graph of e to the power of x looks like this. On the calculator we have e here and here. So why is e a special number in maths, a special constant? Okay, to explain that we need to look at graphs of functions and graphs of the derivative of the function. So an easy example, if we look at the graph of x squared, y equals x squared, the graph of the derivative of x squared, which is 2x, looks like this, and we can clearly see that these are different. There's no similarity between them. Now the graph of 2 to the power of x looks similar to the graph of the derivative of 2 to the power of x, which is this. And if we put both graphs together, we get this. And here we can see that the derivative graph is below the graph of the actual function, which is on the top. This is what you get when the base is a 2. The derivative is below. If I use a different base, let's say 3 to the power of x, you'll see that these two are the other way round, like this. But they still have a similar shape. So we've gone from this, where the derivative is underneath, for 2 to the power of x, base 2, and when we have base 3, the derivative is on the top. So perhaps there's a value for the base between 2 and 3 for which the function and derivative have identical graphs, and that value is e. So e to the power of x and its derivative are exactly the same, which is what makes the value e a special mathematical constant. So if we're looking at derivatives, y equals e to the power of x, so dy by dx is equal to e to the power of x. These are exactly the same. And I could have used function notation here as well, f of x equals and f dash x equals on this side. They are exactly the same, only for e to the power of x. If you have something slightly different, e to the power of and then any function of x, so now my function here, it could be x, it could be x squared, cubic function, a trig function, anything. This formula is more useful, and the derivative this time, if you look at the e to the power of f of x on the left hand side, you'll see that it's also present on the right hand side, but then we multiply by this part. So you look at the exponent, the power, you differentiate the power, it will give you f dash x when you differentiate the power, and you multiply by it. So example 1, part A, if we differentiate e to the power of 3x, we get e to the power of 3x again, but then we have to differentiate the power. If we differentiate 3x, we get 3, we need to multiply by 3. Part B, again we differentiate e to the power of our function of x, so we get that again in the derivative, but now we need to differentiate 1 minus x squared. If you differentiate 1, you get 0. If we differentiate minus x squared, we get minus 2x, and we're multiplying by that. Okay, differentiating e to the power of 3x squared, so there's the e to the power of 3x squared again, just for that term, and then you differentiate just the power. If you differentiate 3x squared, you get 6x, and we're multiplying by it. Differentiate e to the x gives you e to the x. Differentiate minus 4x, you get minus 4. Differentiate a constant, you get 0. Example 2, we need the equation of the tangent to this curve. So we need the gradient of the curve when x equals 2. We need an x coordinate and a y coordinate. Because the tangent is a straight line, here's the equation of a straight line. So we need to look for these values: an x-coordinate, a y-coordinate, and a gradient. The x-coordinate is 2. To get the y-coordinate, we use the equation y is equal to. We put the value x equals 2 into this here. So e to the power of 6 in its exact form will be the y-coordinate. In most problems, we're looking for the exact values and not rounded values. For the gradient, we do dy by dx, so we differentiate our function. We substitute in x equals 2, so the gradient will be 3e to the power of 6. Substituting the values in, expanding the brackets, and now we have an e to the power of 6 term here and here. So I've added e to the power of 6 on each side, so we're just collecting like terms, simplifying. And we could factorize by taking e to the power of 6 out, or we can leave the final answer in this form. To work out the equation of the normal at x equals 2, well, at x equals 2, we know the x-coordinate, it's the same y-coordinate as before, but the normal is perpendicular to the tangent. So if you flip over your gradient from before and change the sign, then if you put them all into our equation of a straight line and then simplify. Example 3, what are the values of a and b? Well, if we take the function a e to the power of 3x and we move this function up by 2 units, so the asymptote, which was on the x-axis for a e to the power of 3x, if we move everything up by 2 units, the asymptote is now going through y equals 2. So this here, the plus b, represents the translation in the positive y direction, and we've moved everything up by 2 units, so b is equal to 2. Now we know the coordinates of this point, which is our y-intercept, is 0, 8. If we substitute those values into the equation, and then rearrange to work out what a is equal to. So we have this. Example 4, find the values of the constants a and k. Okay, so what I've done here is the indices here are being added, which means this term came from the product of these two terms, e to the 5x times e to the power of 3. So I've just rearranged them. So I've put the constant first, e to the power of 3 is a constant. And if I compare these to our terms here, so the a is a constant, which is e to the power of 3. And if we compare these two terms, we can see that the k will be 5. For practice, try these questions.